Greetings everyone, my name is Rohit Udhwani. I'm currently a third year mechatronics student at Asia Pacific University. In this presentation, I'll be going in depth into the history, the creation, and the future of one of the most important inventions that shaped the modern day computer integrated world as we know it. In my opinion, it's one of the most important inventions of all of history. This invention is the transistor. Now, the transistor is something that I'm pretty sure almost all of us have heard about in one form or another. They exist in the cars we drive to work, they exist in the smartphones we own, they exist in the watches we wear, and they even exist in this air conditioning remote I have over here. Transistors are literally, in my opinion, the building blocks of the modern world. And we're in an age of incredible development, exponential development. And it's also called the age of information by a lot of people. And based on a study that was conducted in January 2021, about 60% of the world's population is connected to the internet. That is mind-boggling. And at the core of this whole smartphone and internet-equipped generation lies one single device, and that's a transistor. So the question then comes to this: how did one single invention change the world so much? To begin to understand this, we need to take a trip down memory lane to before the time transistors even existed, to its predecessor, the vacuum tube. Before the transistor existed, and that's also before modern-day computation existed, we used something called vacuum tubes. For the musicians out there, you guys have heard about it in the form of guitar amplifiers because vacuum tubes can also amplify an incoming signal. These vacuum tubes were used inside computers that were the size of entire rooms and consisted of a lot of mechanical moving parts such as gears, motors, levers, etc. Now, the vacuum tube itself, as you can see over here, was a bulky evacuated glass tube that consisted of three main parts: the cathode, the anode, and the grid, which lies between the cathode and the anode. The cathode is the negatively charged part, and the anode is a positively charged part. When electricity is applied to the cathode, it begins to heat up, just like what happens in the light bulb. When it begins to heat up, a process called thermionic emission releases electrons. These electrons are negatively charged particles, and just like everything in nature, they are attracted to the positively charged anode, so they move from the cathode to the anode. This movement of the electrons from the cathode to the anode completes the electrical circuit, and therefore a current flows through. Now the grid in between controls the amount of electrons that can flow through, so it's sort of a controlling mechanism. A caveat to this, however, is that the vacuum tube will only be functional when there's a specific sort of voltage applied to it. So, well, we can use it as to our advantage. We can use this thing to our advantage. In fact, we can use this vacuum tube as a switch. The vacuum tube will only be switched on when there's a specific voltage applied to it, and will be switched off otherwise. In fact, this is the very basis for binary coding, because the on state can be considered as a 1 and the off state can be considered as a 0. And guess what? Literally every single thing in the world is made up of 1s and zeros right now. The video you're watching, the audio that you're hearing out of your headphones, the smartphone you're using, and yes, even this, every single thing is a string of 1s and zeros. One of the first computers ever built was called the ENIAC. It was developed by John Mockley and J. Prescott Eckert in 1945 during the Second World War, and it helped allow enemy trajectories to be calculated. And it worked quite similar to Alan Turing's Christopher, if you've seen the Imitation Game from 2014. Now, the ENIAC reduced calculation times from 1 or 2 days to about 30 minutes. But now you can imagine that the fact that ENIAC was so big, it consisted of 18,000 vacuum tubes, 70,000 resistors, and about 30,000 diodes. Since it was so big, it was extremely power consuming, it was also complicated to build, it filled up an entire room, and moreover it would heat up so much that the vacuum tubes failed frequently and had to be replaced. Despite all of those vacuum tubes, the ENIAC still wouldn't be able to compete against a phone from 2010. That's a bit of a problem, isn't it? Today, that sort of processing power can be contained in a microchip no larger than a grain of salt. So, the question then comes to this again. How does the existence of a transistor allow us to go from a computer that was the size of a massive room to a computer that's no larger than a 50-cent coin over here, as you can see? Well, to understand this, we need to understand the history and the development of the transistor. In 1947, William Shockley, John Bardeen, and Walter Bratton developed the first ever transistor at the American Bell Laboratories. Their creation was much smaller than the vacuum tubes, and it only uses a fraction of the power, all of this while maintaining the same sort of functionality. So how do they work? Well, some of you might have seen one of these bipolar junction transistors, or BJTs, lying around. in your green kids, and you might have used some of them in a project. But they're discrete components and they're about this much. And they're quite large and they're used as a hobby grade project. But the transistors found in your phone or your computer are much, much smaller. In fact, they're microscopic and there can be billions of them on a single microchip. They're etched onto a layer of silicon, which is called thin silicon sheet, which is called wafer, and it's done so by using a process called photolithography. So the key to this transistor's functionality is semiconductor silicon. Now, silicon is a semiconductor because it conducts electricity better than insulators, but not as well as metals. So silicon is important because of the fact that its conducting properties can be changed or altered or tailored based on the user's requirement. It's done by a process called doping. I know it's not what you think it is. Doping is a process by which a foreign impurity is added to silicon, altering its behavior. To explain this better, I'd like to show you what silicon actually looks like. So silicon is a semiconductor. It consists of 4 electrons in its outer shell. Now, keep in mind that this is not a stable state. Atoms need 8 electrons in the outer shell to be stable. Just like everything in nature, silicon seeks to get stability. And it does so by bonding around with its neighboring atoms. And it forms what is known as covalent bonds. These are bonds when electrons are shared between atoms and silicon finally obtains a stable state. In a stable state, silicon is mostly found as quartz and silica and sand, but it's rarely found as a pure metal itself. Now this is where things get a little complicated. If we introduce another element to silicon, we can change the ability of silicon to be able to conduct electricity. For example, adding the dopant phosphorus, which contains 5 electrons in the outer shell, changes the way silicon behaves because now there's one extra electron which is free to roam around from one atom to the other. This sort of dope semiconductor is called an N-type semiconductor, where the N stands for the negative charge provided by the electron inside. Another dopant that can be added is called boron, which consists of 3 electrons in its outer shell. Now, since boron consists of 3 electrons in its outer shell, the structure needs to gain 1 electron to achieve stability. What boron does is then it steals or borrows electrons from neighboring atoms and it moves them to that atom. But what this does is it creates this moving pole of positive charge where there's a lack of 1 electron all around. This sort of semiconductor is called a p-type semiconductor, where this p stands for the positive charge provided by the single pole. Now keep in mind that both of them are actually neutrally charged. The p and the n-type name comes from the p and the n-type charges they have inside of them. Now if we take a look at the n-type silicon and the p-type silicon and combine them so they look like this, we've created the very first bipolar junction transistor, similar to what William Shockley created in 1947. So how does it work exactly? Because by itself, the N, P, and N semiconductors are pretty useless. So when you connect the N, P, and N in this form, the extra electrons from the N-type semiconductor move to the P-type semiconductor, filling up the holes. But this movement of electrons from the N-type to the P-type causes what is known as a depletion layer. Now this depletion layer gets larger and larger until electrons officially stop moving because there's no more space for the electrons to go into. Well, what happens next? We apply a positive voltage to the P-type semiconductor. This allows electrons to move from the N-type semiconductor to the P-type semiconductor again, reducing the depletion layer. Now, what happens now is that the electrons are freely moving and there's a current flowing through the semiconductor. We've actually created a semiconductor that fully works. And do you remember what I said about a vacuum tube consisting of an on state and an off state? Well, the same can be applied over here as well. A transistor in an on state can be considered as a 1, whereas a transistor in its off state can be considered as a 0. So, all of this, and the question is, this is just a switch, similar to what a vacuum tube is, right? But how does a switch help us get to where we are today? Well, you see, computers don't necessarily think like humans do, and they don't use the same sort of logic that humans do. Computers use something called Boolean logic, which is a logic that's developed and based on zeros and ones only. But the sort of circuits they use is also completely different, and the way they do calculations is different too. So, for example, doing a simple calculation such as 5 plus 6, which results in 11 for us, would be a very different process for a computer. A computer requires a circuit called a half adder, which is made up of an AND gate and an OR gate combined together. Now the problem with this is that millions of calculations like these requires millions of different circuits to function together. With the need for higher computing power increasing every single year, computer engineers that were developing these initial computers with discrete transistors were having a nightmare because of the fact that the number of transistors increased every single year. The solution to this problem was presented by Jack Kirby in 1958 and was improved by Robert Noyce in 1959. This thing was called the integrated circuit, similar to what's over here. The integrated circuit managed to combine several transistors into one single component, rather than having all of them being soldered individually, similar to what you can see over here. Now this integrated circuit is made of silicon, similar to the transistors themselves. Now here's the thing, early integrated circuits, early ICs that is, consisted of about 5 to 10 transistors at best. We changed to a few thousand by the late 1970s, and we changed to a million by the early 1990s. And right now we're living in the age where we're reaching about a trillion for one single integrated circuit. As you can see over here, this is a 16-pin integrated circuit that consists probably of millions of different transistors inside of it to achieve a specific sort of functionality. A single integrated circuit inside of your phone can consist of billions of these little transistors. That is incredible. This was a pattern that was realized by Gordon Moore in 1965. He said that the number of transistors on an integrated circuit doubles every 2 years while maintaining the same cost. This was later called Moore's Law, and I'll be talking more about this later on. Despite the development of transistors contained within a single IC, within a single integrated circuit, the need to solder and wire these individual integrated circuits together with other components such as resistors and capacitors meant that a lot of wiring and individual soldering still had to be done. To combat this, scientists formulated the printed circuit board, or the PCB. In this, the wires were built into the circuit board itself, so there's no need for external wiring or external connections, similar to what you can see over here. Instead, all of the components required could directly be placed into the board itself, which removed the need for external wiring and made circuits a lot simpler and better. The progression from vacuum tube to transistor to integrated circuit and to printed circuit boards was something that took the entire world by storm. The improvement not only highlighted a new age of computing, but it also allowed humans to reach for things they never did, such as reach for another planet. For example, we finally were able to send humans to Moon in 1969 thanks to transistors. It boosted computer production and reduced the cost and the size of the computers that were being produced, all of that while increasing the processing abilities of these computers. By the early 1990s, almost every single device consisted of a transistor in one form or another. From watches to TVs to radios to satellites, literally every single device consisted of a transistor. For example, the speaker I have over here consists of many, many different transistors combined together in an integrated circuit. It receives Bluetooth audio, amplifies the Bluetooth audio, and puts it out to the speaker. In 2013, a research team studied that Moore's Law was in fact true, and it was coming to an end very soon. In 2016, Intel expressed concerns over shrinking the size of transistors to beyond a certain point, and also expressed concerns over the increasing costs of producing microchips because of the amount of research and development that goes into them. Transistors have shrunk down from 0.8 microns to 5 nanometers today. However, forecasts made by experts such as Mr. Gordon Moore himself say that this will soon cease to exist, and that it as soon as 2025. The problem is because of the physical limitations of building small transistors itself. The problem comes to this. Well, transistors tend to use electrons to move signal from one point to another, but you can only go as small as the electron is, which is about 1/25 trillionth of an inch, because even reaching those limits would mean that issues such as quantum tunneling prove to be an issue. This is something straight out of a movie, and we're reaching a level of development where we as humans can say that the electrons are getting too big for us. The future of current transistors is a bit hazy, to be honest. We'll soon be hitting a brick wall, and we'll not be able to make any advancements for a little while. But study for alternatives is already underway, such as quantum computing, which adds another state besides the 0 and the 1, and improving the architecture of integrated circuits and improving the processing abilities of microchips. things such as Internet of Things is being placed, which requires lesser processing power and more of a distribution of the Internet. While we're reaching the limits of transistors, computing developments do not seem to come to an end. Uh, but despite all of those problems, the future doesn't seem to be dull for these little devices. New emerging technologies will always be at our hurdle, from a capital implementation and from a conceptual standpoint. However, it is true that something might soon replace a transistor, just like how the transistor replaced the vacuum tube. But we still don't know the necessary amount of time required to be able to change these little ingenious little devices. And we don't know if we have the viable technologies yet. However, we won't be able to replace these ingenious devices anytime soon. Here's the transistors, holding up modern society with their base, their imaging potential, and their controlling praise. Thank you so much.